Hello everyone, welcome back to our YouTube channel, Becoming a ROS Developer. So today we've got one of our students, Stavros, who has managed to complete the course Python 3 Basics for Robotics. And he will take us through how he managed to do his presentation, his project. But before that, he will do a demonstration of his code base working on a real robot. And then we'll get into the nitty-gritties about the details after that. So I'll hand over the floor now to Stavros and he can begin his presentation. Over to you, Stavros.
Okay. Hello, everyone. Give me a second because we have not yet access to the robot.
All right.
So let's begin by explaining some code here. Let's start with the non-object oriented programming. Here are the definition of the functions to get some information about the robot. For the robot movement, here we give linear velocity, angular velocity, here how to stop the robot, how to move the robot. It's pretty straightforward. And here we have some laser scanner functions to get the info from the scanners. And now I see that I have a connection to the robots, so let me just do this for a sec. And first I will demonstrate the non-object oriented programming to see how the functions correspond, to check if everything is okay, and we will move to the next version.
All right.
Okay, we're connected.
All right.
Okay, let me quickly connect. Okay, now I'll have to go to the directory that I have the files.
All right.
Okay, there they are. So first we will execute the non-object oriented one.
Okay.
With no classes, that is. Okay, well, I should first rearrange the robot, but I think we'll be fine. So here you will see different details printing on the screen. I have arranged that so we get some useful tips for when a function is checked and what is being done during the check.
Mm-hmm.
We check every function. Now it's turning left. Now it's turning right. You should see the robot corresponding to that.
Okay.
Here is the timed distance front. So I have predefined the duration in 5 seconds. So we see here. Now it goes backwards. Again, time back check.
All right.
Now it turns to the one side, it turns to the other side. Okay, now we move forward to a distance. I hope it won't crash. Okay, just I should rearrange the robot. Okay, and we also see the Euclidean distance. The desired distance was 0.5 meters. The Euclidean distance is 0.48. You know, some little error there.
Okay.
And that's turning left 45 degrees or 0.78 radians. We also see the orientation. It's not exact, but that's okay. We also see here the laser scanner functions. I will come back to that after the functions is finished to check more.
Okay.
So here we check the geometry, the Euclidean distance again, the kind of orientation. We turn the robot so you can see that orientation changes.
Mm-hmm.
And okay, now it should be over. We check the IMU, the angular velocity, which for some reason here doesn't show anything, but in the next program you will see that it shows the angular velocity. So to come back to here, we see the ranges lists with the minimum range, maximum range, etc.
Mm-hmm.
And see the index value. I have chosen the one, so the second value of the list, which is 1.516. This is 1.516. The front scan, the back scan, which is corresponded to different list, different index on the list.
Mm-hmm.
And okay, that's all we have to do for this version. And now to run the um, object-oriented programming, which means we have classes in this program. First, we will just let it run. Now we see the robot is in front of an obstacle, so it should stop, as we see here.
Mm-hmm.
I have again set it up so we can print different information. Okay, so it now detects the further distance from left or from right whenever it has an object in front of it, and turns to the different distance, the different side. Okay, now it has turned. So let's let it run for some time now. Here it prints a non-object because there is nothing in front of it. The
Right.
calendar and acceleration, which isn't very useful because we can see it's steady. It goes 0.05. Some change there, the orientation and the tracking for direction.
Yeah.
It was going west for some time. Now it can change. It goes northeast, and yeah. And for what I understand is, if we see the left picture here, the left camera, the
Mm-hmm.
north is this way that the robot goes, and east is left, and west is right. And okay, so here we have some more information. Here it checks the front right side. It sees that it's lower, so it turns left. That's what it's been done here. Now it had detected the front right obstacle and turn left, and so on. Okay, so I will keep the robot running, and I am going to explain some of the code for the class one. Let
Okay.
me close this one.
Can you maximize that a
Okay,
little bit so we can see it all the way to the
of
bottom?
course. Okay, here's the class. I called it robot control, which is familiar from other courses.
Mm-hmm.
And here are the functions defined inside this robot class. It's the same as the non-object oriented one, but this program has some benefits because it keeps the program a little more clear to the eye. But I haven't done that in this program. We could define all the functions that you see here in this program and then create a new to just call the class from this program to execute in the other program. But now I have compacted all of these things in this program for now. So the important part for this program is that I have included this part 3 that I have called it, which is the robot algorithm. It has 3 algorithms, one for obstacle prediction,
Mm-hmm.
which it's easy to understand. We just have to get uh, a cone, if you imagine, in front of the robot at 90-degree angle,
Okay.
and that's what we do in this line of code. We get the list of all the ranges, the list that we saw previously,
Okay.
and these ranges are for the front of the robot. And now we have to exclude the infinite values, which I had some problems with trying to do it myself. So I just searched online, tried different things, and I chose this one, which uses the lambda function, which go through each item on the list, the filter function, which keeps the value in variable t, which we see is a math.inf, and the list just creates a list for this purpose. Now we go through the new list that we built without the int values, if there is any,
Mm-hmm.
and we create a variable with min value equal to 100, something big that can be replaced with the minimum value that is being done in here, in this while loop. And since we get the minimum value from this loop, we just have to compare it with our threshold. Our threshold for now is 0.3 meters, as included in the project. If it's bigger than that, we print none. If you saw here, um, it prints none object ahead. Or if it's not, if it's less than the threshold, then it uses the statistic library with the multi-board function in this list to see how often some values can appear in the list. And if the length of this list is bigger than 1, that means that there are a lot of values that appear often. It means that there is an obstacle. So there is a range of values in the list. Or if is or if the other case, in the other case, it prints a wall. That means that different values don't exist. It's a standard value. So yeah, that's not pretty accurate to say, but that's okay for this project. So we go through the next algorithm, which is the direction tracking. The direction tracking just tracks where the robot is headed. Here you can see it here. It goes southwest for now. And here I just have to call the function that we created earlier for the car orientation and just store the yaw orientation, which is the z-axis of the robots, in some variable. And then we just have to classify the different ranges, which has been done here for the different cases, as you can see. And now for the third algorithm, which is the main algorithm for the wall avoider, or the naive wall avoider. I don't remember exactly how to say it. I have chosen to, as a start, I have chosen to run only once the instance of the class, so we can call the different function we just created to get the current position of the robot before it starts moving. And here it's an algorithm, if you may, for to get the current ray values for the first time. So the robot gets the laser values for the left side, right side, front left, front right, and front for the different ranges I have declared here. And here just go through to get the minimum value out of them. And yeah, it stores them in these variables that we see here: L left, L from left, the list front, list right, etc. And for the continuous loop, I have this program built, which just checks if as long as the list front is bigger or equal than our threshold, 0.3, it will just move ahead. But before it does that, it checks that if the front left is lower than our threshold, it will go in, it will stop the robot if it's moving, it will turn right for some amount of time, it will print the current angular velocity, which in this case, you should be seeing some results here. It was so fast that we didn't see it anyway, but it prints the turning angle. It's negative 0.5 because it's right, it's counterclockwise.
Okay.
And here we take the current position of the robot, which is the second position from the one it's moved in, to get the Euclidean distance, to see how much time, how distance has it covered. It has covered from point A to point B before it stopped.
Okay.
Now we store the current position to the x1 and y1, which is the first variables in Euclidean distance. So from the next step, we get again the x2 and y2 from again calling the current position and calculating the Euclidean distance again. Here is the same algorithm as we saw in the first execution, because it constantly has to update the values of the laser to see how close or how far it is from the objects. Here's the second case, which has exactly the same. It does exactly the same thing, but now it turns left, not right, because there is an object on its right side.
All right.
And here we in the main while loop before we call the obstacle prediction function, which will print if there is an object ahead or if it isn't.
Okay.
The Carolingian acceleration to provide some information, the direction tracking to see where the robot is heading, and to move the robot, of course.
Right. I see.
Again, here the algorithm. Excuse me.
I just said I see. All right.
Oh, okay. Sorry, I thought you meant you want to see the robot performing. Okay. Here is again the algorithm to check online. So now we go to the second case where if there is an obstacle ahead, we have the program print object front to realize that there is something in front of it. Stop the robot, again, get the car in position, the same thing, calculate the Euclidean distance, and now don't check front left or front right, just check the left and right side of the robot and turn towards the side that has the greatest distance.
Okay. Okay.
It does the exact same thing, just calling the timed right function now, which is to turn the robot for some seconds.
Okay. I see.
Okay, and this is the other case to turn left. Okay, and this is the one where if all the ranges of the robot are blocked, we just say turn to the greater side again, but turn for a greater amount of time to just literally turn around the robots and move out of the wall.
Okay. Okay.
Okay, and that's it. So let's see the robot, how it's doing. Okay, that's it for me.
All right.
I
All
hope I
right.
covered everything.
So that was both the non-object oriented version and the object oriented version, right?
Okay, yes, yes.
All right. All right. Well done on the nice explanations that we've given there, and also very clear explanations on how you are managing to do obstacle avoidance in those control loops, right? And
Mm-hmm.
so on just general questions, right? I would want to find out from you, being the person who is implementing this in the two contexts, right? The non-object oriented way and the object oriented way. What benefits did you find um, uh, from any of the implementations, right? So I cannot say object oriented
Mm-hmm.
or the non-object oriented version, right? Because it depends on your scenario. So which one was better for you?
Yeah.
And can you explain why it was better?
Okay, yeah, sure. Well, as I have learned through the courses, of course, it's a matter of scope, as you said,
Mm-hmm.
depending the scenario. In this case, I think both scenarios are useful. The both scenarios can get the job done, but as you saw, the functions are too many, and
Okay.
there are too many, yes, and the code was a little bit messy. So the class function, the object-oriented programming, I believe it's much better because you can clearly organize, even though I didn't do that as well, although I explained a little bit, because you can create the class in one program and you have all the functions there,
Mm-hmm.
and in another program, you only have to call the desired class
Right.
um, from the program you created, and it's just clear. No functions in that program. You can call it anytime you want, any functions you want, and it's much easier to see and understand what it's been done. Here, if I hadn't explained this how much it's been done and haven't commented, it's a mess. You can't understand what is being done. You need your time to understand
Right. Right.
the program.
All right. All right. I see. Yeah.
So yeah,
So from this, I'm getting the fact that you found the object-oriented implementation a lot clearer, cleaner, also, and
cleaner.
yes, for
Sorry, sure,
the
yeah, okay, it's right.
future
Cleaner.
person who reads your code, right? Even if it's the future you, that would have been a good option on that basis, right?
Sure, sure.
All right.
Again, depending on the scenario, if it's something simple, you could go with the procedural one,
Mm-hmm.
the non-object.
All right. My next question is there is something you mentioned that you struggled with. What was
Mhm.
it exactly? I think it was.
Yes, yes. Let me tell you, it was about the obstacle prediction. I struggle a little with excluding the inf values of the list. I tried different methods, which I thought they would work, but they didn't. And yeah, this command right here, I found it online after some search,
Okay.
and I wanted to see what it does, and
Right.
I understood it,
I see.
and Yeah, I also found another command, but it wasn't suitable for this case because it was the commands with the function set, if you're familiar with, and that command, that line was only getting the values that was showing, and it stored them just one time. And if one value was appearing twice or more, it just stored them one time, and that wasn't working for us because we needed the stats list to do that for us if it appears for one time or more times to
Okay,
see
I see.
if there is an obstacle or a wall in front.
All right. So you were trying to eliminate the not a number values that we're getting from the laser scan data.
Mhm.
Right. I see. I see. And then having to do it using this function proved to be difficult.
No, this function was pretty easy. I tried different ways myself, and I
Okay.
find it
And
difficult to
then
do it
you did.
alone because
I see. I see. And then this
yeah,
one
yeah.
was the
When I
one that
find this
finally
one,
worked.
yes, it finally worked. Although I have tried, as I said, different ones. But yeah, I chose this one. I'm sure there is a better way to do it, but
Well,
uh,
I think
this one do the trick.
it works quite well, and it's short. You understand it. It's easier to for anyone who reads the code to kind of understand what's going on. So I would say good,
Mhm.
well done on the on looking it up to find one that would be simple enough to understand, and also at the same time making getting the job done, right? Getting the job done.
Yeah.
Um,
Mhm.
so the other question that I wanted to ask you about is where is that bit? Okay, the statistics lib. You mentioned using the statistics library. Can you get into the details about why you had to opt for that? What?
It was yeah, that statistics library wasn't my intention. It was instructed into the project. We
Mm-hmm.
needed to use that so we can define if there is an obstacle or a wall ahead. So yeah, that wasn't my idea.
Yeah,
It
yeah, yeah.
was the courses. Yeah.
Yes, I understand that. I just want to see if you understand the basis of having to use it. That's where I'm getting to.
Oh, yeah, I understand it as I mentioned, as I explained, that this function, the statistics dot multimode or the list, just returns a list with different values. If the values inside the f scan no inf list that I've created here, um, there exists only one value that appears all the time. The length will return as one. That the list has only one value in it,
Okay.
and that's the same. So that means that there's a wall ahead because, as I understand it, the wall is flat,
So
and
the
different ranges um, detect the same value more or less.
right. Okay. Wonderful. Wonderful. That's
But
yeah.
yeah,
That's where I wanted you to get to so that we get the fundamentals of what we're getting out of that function, which comes from the
of
statistics
course.
lib. Yeah. All right. So
Mhm.
let me see if I have any more questions. That's it on my part. So I would say very well done. Explained
Thank
nicely,
you.
and also it took us through your code step by step. Um,
Mhm.
so I'll say that was very nice. Congratulations on that. So I will just do a wrap up now, and then we can finish our meeting on Zoom.
Sure. Do I need to stop sharing
Mm,
or
yeah, it's fine. All right,
okay?
everyone. So this was Stavros' presentation, and we would like to say congratulations to him on the job well done, good explanations, and also taking us through what he learned from having to approach the project with different methods, object-oriented programming, and the non-object-oriented versions. So we encourage everyone who would like to take one of the courses that we offer certification on to give it a shot, and then you'd have your chance to make a presentation and also give a detailed explanation of why you think your method is good for that. So until next time, keep pushing.